Let's consider an example as we search for absolute extrema. Now, the last problem covered the construct where we were interested in relative extrema because we could compute critical points. Now, remember back in Calculus 1, when you would have a closed bounded set and a continuous function. Well, the extreme value theorem said there is a definite max and min on that set. Now, of course, that doesn't give you a algorithm to solve for the particular extrema. That is, you know they exist, and so then you think, well, what other ingredient do we need? Well, that's where Fermat's theorem came in that said if a function has a relative extremum, it must occur at a critical number, or in our case, critical point. So we could combine utilizing the critical numbers, so to speak, with the endpoints. Now, when we consider a function of two variables, we can consider the existence of any critical points with the boundary. So with that small adjustment, we can take the same technique from Calculus 1 and apply it to a function of two variables. So here's an example that I think you'll find to be very illuminating and actually quite simple. What we want to do is find absolute extrema for f equals 14 minus 3x minus 2y. That's the function right there, where R, the actual region, is the triangular region in the xy plane with vertices 2, 0, 0, 1, and 1, 2. Now, just before we do any analysis, I want to put to rest the critical points. Now here I'm going to go to the next page and then we'll come back. Notice when we take the x and y partials, we get constants. So there are no critical points. It's like we're in Cal 1 and we look for interior critical numbers, they don't exist. So here we have no critical points, no horizontal tangent planes. Well, what we notice is that this function defines a plane. So we don't expect that we would actually have critical points. So using the technique from Calculus 1, we look to the boundary of the region. So now we can go back to the problem and it just becomes a college algebra problem, which of course you're thinking, well, why do we need, to do this problem? Well, it's actually very important because you never know what you're going to have in a math problem or an engineering problem or a science problem. So now the key here is to simply construct the boundaries. So notice I've labeled the points here, and I've also labeled the line segments of the region R by a 1, a 2, and a 3. So here's the analysis, very simple. 2 points determine a line. So when you look at 1, we can just look at rise over run. So we have 1 minus 0 divided by 0 minus 2, which gives us a slope of -1/2. And now, of course, you can be lazy, you can use either point, but notice here we have y equals -1/2 times x minus 2 if we use this point. And then if you multiply, you get what? A -1/2 plus a 1. So now notice this is the actual expression for y in terms of x for 1. Okay, so we're going to do the same for the other two, and then we're going to use these expressions to rewrite the function f. Now, with the same procedure for the points 2, 0, and 1, 2, you can do the same. Rise over run, 2 minus 0 divided by 1 minus 2 gives you a slope of -2. And now again, you can use this point because it's easy. So you get y equals -2 times x minus 2, just using point slope. And then, of course, if you multiply, you get y equals -2x plus 4. Now notice, as I've done here, when you see 1, you see that X runs from 0 to 2, and I've noted that here. In this particular case, for the second boundary segment, X is running from 1 to 2, which I've noted here. Okay, just very simple, but maybe not something that you would think about doing. Now, for the other line segment, again, you can use whichever you like. 2 minus 1, 1 minus 0 just gives you a rise over run of 1. And so you can use this point and we get what y equals x plus 1. Now, of course, you don't have to just take things for granted. Always check the points that you have to make sure if you substitute 0, you do get 1 as we do. If you substitute 1 for x, you get 2. So always check the algebra, even though it's very simple, it's very important. So now what we want to do is take the expressions for y and substitute them into f so we get a function of one variable. But in every case, we're going to see that the result is a linear function, and those are simple to optimize. So for instance, for segment 1 here, we just simply replace y with the expression negative 1/2 x plus 1, which I have here. And then we, of course, multiply. So we get a positive x, and then a negative 2 times the 1 is a negative 2, and combine terms. So we have 12 minus 2x. Again, same restrictions on x. X runs from 0 to 2. Okay, well, this is a linear function, and it's decreasing. So the maximum must be at the left endpoint, and the minimum must be at the right endpoint. So we just substitute 0 to get the max, we get 12, and we substitute 2 to get the min, and we get 12 minus 4, which is 8. Now, notice I've got 2 red boxes here, and they'll make sense as we move through the problem. Now again, what I've noted here is that the endpoints that we're using. So of course, if we needed to find y, we would, but you notice I don't care about y, and that will become clear as we work through the problem. Now for number 2, again, y is negative 2x plus 4. So everywhere we have the y, we substitute that. And so that's going to give us a negative of 4x and also a negative 8. So if we combine with the terms, this is going to give us what, a 6 as a constant term, and then of course an x as the variable term. But now this is an increasing function, so the maximum will occur at the right endpoint and the minimum will occur at the left endpoint. So when x is 2, we get a maximum of 8. When x is 1, we get a minimum of 7. Notice I put a red box around that. As we do the next one, it will be clear why I did that. Now, just to be clear, with this red box, if x is 1, we can easily find y, because we know that y is negative 2x plus 4. So we just substitute 1 for x, and we get y is equal to 2. And so we have an ordered triple, 1, 2, 7. Okay, let's move to 3, the other component of the boundary. Again, in this case, we have a rise over run, as I said before, equal to 1, and we ended up with y equal x plus 1. So now we just substitute into the function. Again, we have negative 2 times x plus 1. That gives us a negative 2x minus a 2. And then when we combine like terms, we have a negative 5x and we have a 12. Now notice in this particular case, x is running from 0 to 1, but again, this is a decreasing function. So the maximum will be at the left endpoint and the minimum will be at the right endpoint. So again, when x is 1, we get the minimum of 11, and when x is 0, we get the maximum of 12. Now, when you look at all of these numbers, the largest number is indeed 12, and the smallest number is 7. That's why they have red boxes around them. And now, of course, when x is 0, if we go right back up to here, we see y is equal to 1, and so we get the ordered triple 0, 1, 12. Now, this is a really good example because it's exactly calculus 1, but it's calculus 1 applied 3 times. Again, you look to the boundary when you have no critical points. That is, this is a closed bounded set, and you have a definite continuous function here, y equal 14 minus 3x minus 2y. By the extreme value theorem, you know there is a maximum and a minimum. And all we have to do is look on the boundary. So now what I've done on the second sheet, which I didn't refer to before, is just summarize. Since we had nothing to look for on the interior, we simply now have the maximum of 12, which occurs at x equals 0 and y equal 1, and we have the minimum of 7, which occurs at x equal 1 and y equal 2. So again, the word absolute is just a way to keep you from thinking relative. But if you say maximum or you say minimum, that really by definition means absolute. But we like absolute because it makes us feel better that we actually did the right strategy in the problem. So again, in summary, when you have a closed bounded set and a continuous function, you check for the existence of critical points. If you have them, fine. If you don't, then you look to the boundary. And so the technique would be to convert the function of two variables to one variable by analyzing the boundaries, like we've done here. And then you have a very simple calculus 1 problem and a result that, though it seems complicated, is actually quite simple. And we are done.